So today we have one section, which is kind of exciting. I would be shocked if this one section takes all 3 hours, which is good. That said, there's a reason there's only one section. This is such a massive topic, and it is such an important topic. It also, which is going to be music to some of your ears and sadness to others of you, this relies heavily on pre-college algebra topics such as factoring. And we have yet to get into factoring really this semester. We've talked about greatest common factors, but the other type of factoring techniques we've yet to even touch. So I'm going to try to introduce them. Hopefully it sparks a memory, sparks some things you already know, but if it doesn't, it's going to require you to learn some things on top of this specifically. So that's why we're doing just this section today. First thing, very first thing that we need to be comfortable with is vocab and language. And I've already told you the relationship between these words, but we have to at least mention it today. Otherwise, the questions we're asked, they're going to seem like they're just drastically different, and they're actually all the same. So please be extra aware that solutions are the same thing as roots are the same things as zeros. Those are all the same idea. Those are the locations where the graph crosses the x-axis. So you'll also hear x-intercepts being equated to those things. So all of those four terms mean the same thing, granted they are real. Now, if they're not real, there's a breakdown right here. Last week, we talked about complex numbers. If they're complex, clearly they couldn't be on the x-axis. It wouldn't be an x-intercept technically. So these are only, this statement here is only true if they are all real. So if you want to make a note of that or something, that's when it's real. And this is always true, regardless of whether it's real or complex. So just a brief distinction there, but the takeaway is regardless of what it's asking for, these would all be the same procedure. I'll go ahead and number that one because there's a couple other things we probably talk about before we get into this too far. The second thing is this lovely fact of mathematics called the zero product property. And this is also something very, very important that came to you prior to this moment, or should have been taught to you prior to this moment, that we're going to use a ton today. So briefly, and I won't get into like the full on definition of this, but I'll just briefly tell you what the zero product property is. The zero product property says if you take A times B and it equals 0, then you have learned something very profound about A and or B. And that's because we know in mathematics, if we multiply two things together, and that's why we're using A and B, this literally means anything. If you multiply two of anything together and it equals 0, we know from math that either A is 0 or B is 0, or they're both 0. And that's exactly what the zero product property tells us. So again, if we know that two things multiplied times each other equals 0, then either the first thing is 0, the second thing is 0, or perhaps they're both 0. So zero product property is going to be very, very important to us today. And the third fact that we need to be aware of is the difference between two essential vocab words here. We already talked about solutions and what exactly we're talking about there, roots, zeros, x-intercepts. Those are numbers, right? Where does a graph cross the x-axis? It crosses at 7 and 2 or something like that. Those are just numerical values. So what we need to make sure we understand is the difference between factors and solutions and how they are not the same. Factors are something different. Factors are the things that multiply to make whatever you're talking about. Solutions are not that. Solutions are zeros, roots, and x-intercepts. And what happens is students end up getting those confused, but you'll notice factors is not listed anywhere in that list there. It's because they're different. Now, Why they get confused so often is there's a relationship between these two things. And we need to know that relationship, but we've got to make sure we can differentiate in between the two. And I'm going to give you just a quick couple examples here of the relationship. So, for example, let's say 4 is a solution. Let's say we solved an equation and we got 4 back out. If it talks about the factor that goes with that, we need to make sure we understand that 4 is not the factor. To turn 4 into the factor, we would write it as x minus 4. This is terrible grammar, by the way. 4 is solution. 4 is a solution. That would imply that x minus 4 is a factor. So that's the relationship there. And when I'm talking factor, I'm not talking like factor tree from 3rd grade. I'm not talking like, oh, 2 times 2 is 4. I'm talking about quadratic factors or polynomial factors where you take an equation or you take an expression with a bunch of variables in it, you break it down into its smaller parts. This is what I mean by factor. And that's going to be the goal today, because it turns out solving quadratic equations is heavily influenced by your ability to find factors. So, moral of the story, this is a solution. A numerical value is a solution. In order to turn that numerical value into a factor, it's easy. You just do x minus that number, and then that's the factor. So concept check here. Let's say -3 is a solution. What would its factor be? Well, again, if I followed the convention of x minus the solution, that means my factor that goes with that would be x plus 3. So please notice the difference there. The definition is x minus. So if you end up with a solution that's negative, that would turn the factor into a plus sign. And then the only other thing you really need to be aware of before we get into this is sometimes your solutions aren't whole numbers, they aren't integers, they aren't natural. They could be rational, as in fraction. So we need to make sure we know how to exchange a fraction solution into its factor. So for example, let's say 1/2 is a solution, perfectly legitimate. You could have a function cross the x-axis at 1/2, but we don't want to take a fraction and do x minus 1/2 like we did whole numbers or integer numbers. That's not how that works. So instead, and this is one of these deals where like you just have to know this, you're going to take the denominator of your fraction, which is 2 obviously, multiply that by x, and then subtract the numerator. That's how you turn a fraction into its factor. A denominator times x minus the numerator. Now, if this all seems out of left field, if you read this backwards, it should make more sense to you. If x minus 4 is a factor and we want the solution that goes with it, we end up setting it equal to 0. That is the mathematical convention you've had forever. If you'd like to know where it crosses the x-axis, we would need to know where the function equals 0. If you let x minus 4 equal 0, guess what your solution is? Well, you'd add 4 to both sides. Boom, you get 4. If you set x plus 3 equals 0, you subtract 3 from both sides. Boom, you get -3 for your solution. If you set 2x minus 1 equal to 0, you would need to add 1 and then divide by 2 to get your solution. Guess what that equals? That equals 1/2. So what you're doing here is you're just viewing this in the backwards sense, but this is exactly why that relationship holds. It's because if you were to solve these for x, you would get exactly these numbers. And then just to complete, let's do a negative fraction here. Let's do like -2/5. Let's assume that's our solution. And using that same convention, since it's a fraction, I won't do x minus -2/5. I would do denominator, which is 5, times x minus the numerator. And of course, minus -2 is plus 2. And just like a lot of things in math, if you're ever unsure, like you did this transformation, and you're like, oof, don't know if that's right or not, just go backwards, set that equal to 0 and see if you solve for x, do you indeed get that solution or not? All right, so I know that's a lot of stuff. That's all pre-college algebra type of ideas there, but you need to have a good handle on those three things if you're going to succeed in our goal today of solving quadratic equations and inequalities. If you recall last time when we did 3-1, 3-2, we were doing a bit of this, but the equations we were solving were much simpler. They were just like x squared plus 4 equals 0 or something like that. What we were going to look at today are the more complex ones, more terms involved. And of course, we're still talking about parabolas. That hasn't changed. That's what this whole chapter is about. And we talked about at great length, like x-intercepts on parabolas. Typically, those are your solutions there. Typically, you're going to have two. Now, there are instances where you wouldn't, and we kind of referred to that last time, but generally today, this is what we're looking for. We're looking for those two places. So let's dive in and figure out exactly how we should go about doing this. So we're going to start off with this guy. Solve 3x squared minus 15x plus 18 equals 0. And depending on your memory of Algebra 2 or even Algebra 1, you actually do this in every algebra class, you may be aware already that there are like 3 or 4 ways that you could go about solving this. You could literally draw a picture of this and figure out where it crosses the x-axis. Now, it may not be the nicest of numbers, but you could do it that way. There's also, well, I'm not going to list them because we're going to get into them today, but there are a lot of ways to do this. The first way I'd like to show you is the preferred method, if at all possible. This will not work every time, but it works a lot of the time. And that's utilizing the zero product property, this fact up here. What we want to do is we want to turn our equation, blah, blah, blah equals 0, into blah times blah equals 0. And if I can get it down to this level here, then I know either the first component or the second component, or in fact, both of the components will equal 0. And if you break down a quadratic, you get a linear and a linear, and every single one of you knows how to solve a linear. So that's our goal. First rule of factoring, and this is how we break it down into the components as we factor it. First rule of factoring always, and you can write this down, you can do whatever you want with this, but the first rule is to identify if you have a greatest common factor. If you do, that needs to exit, that needs to be pulled out to begin with. So the question is, do I have one in this equation? The answer is yes. Each and every one of these terms has a greatest common factor. It has a factor of 3. That is the largest thing that I could pull out of those 3 terms. So that's where I'm going to start. So I'm going to pull the 3 out. If you take a 3x squared and pull a 3 out, you're left with an x squared. And when I say pull out, I'm talking about divide out. You're dividing it out to the front. If you pull the 3 out of negative 15x, you're left with a negative 5x. And if you pull a 3 out of 18, you're left with a 6. You're reverse distributing, essentially. At that point, if you're ever like, oof, don't know if I've done that right, just distribute it. And if you get back to the original, you have indeed factored or GCF'd correctly. Now, at this juncture, we're still not all the way down. We are not into linear factors yet. I still have this quadratic term here, so I'm going to have to try to factor that again. And the goal, when you're trying to factor a quadratic like this, you want the number out in front here to be 1. And if that's the case, you can do something that some teachers refer to as reverse FOIL. Basically, it is exactly what it says it is. It undoes the foiling that would have occurred to make this. And there's a little rule that you're hopefully aware of to know whether you can do this or not. You can break this down into 2 factors as long as you can find 2 numbers that multiply to C, but also add to B. So if you can find 2 numbers that multiply to 6 and add to negative 5, then this can be factored using reverse FOIL. Before I get to those 2 numbers, you would need an X here and an X here, and I think you should all be familiar to why that is. If you were to FOIL this X times X, that's what makes that X squared there. Then it's just a matter of what number do I put with this X and what number do I put with this one. Well, hopefully you can all tell me what these are, but the two numbers that multiply to 6 and add to -5 are -3 and -2, right? -3 times -2 is +6, but if you add -3 and -2, you get -5. So that's exactly what I'm going to do. I'm going to put in a -3 and a -2. And by doing that process, you have just undone, you have took apart, essentially, you've taken apart the FOIL. You've undone the FOIL. Again, at this step, especially if you know you are weak at factoring, or I'm doing this and you're like, wow, I don't remember ever seeing that, it's not a bad idea to check this. If you FOIL this back together and multiply each term by 3, you should go right back here. Okay? And if you're familiar with this already, awesome, this won't take you long. But if you're not, this is going to require some practice. It's one of these pre-college algebra skills that you hopefully came installed with, but if not, you got some work to do. While I'm here, since I said that verbally, I will write this down for you guys. You're looking for two numbers that multiply to C, add to B. And obviously, this goes back to what we talked about last week. Standard form, this is your C number, this is your B number. All right, now I've got it down into the factors. And then remember, factors are not solutions. So I'm going to need to go one step further here. And this is where the zero product property comes in. Zero product property says if you have two things that are being multiplied and they equal 0, that indicates either this guy's 0 or this guy's 0, and we're going to assume actually that they're both 0. So at this point, I'm going to set my factors equal to 0. And remember, 3 is a factor. It's called the greatest common factor. I'm just going to go through here and set each and every one equal to 0, courtesy of the zero product property. Now, once I've done that, you've turned this rather complicated problem into a very easy set of problems, right? These are one-step linear solving problems right here. This is like what you learn in day 3 of Algebra 1 type of stuff. Note over here, though, when you set the GCF equal to 0, this is impossible, right? 3 does not equal 0, so you're going to just ignore that. That's not going to be part of your answer, right? 3 is not a solution. 3 cannot be 0, so it's out. But this can be 0. If x minus 3 equals 0, what does that tell you about x? Well, you would add 3 to both sides, which tells you that x could be 3. Same thing on this one. You could add 2 to both sides, which tells you x could be 2. So what you have found here is if you put 3 into this equation, it equals 0, or if you put 2 into this equation, it equals 0. And this is what I was talking about with parabolas. Since solutions are x-intercepts, you are looking for 2 answers most of the time. Not always, but a lot of the time. And of course, could this be checked? Absolutely. If you manually plug those numbers in, like for example, put 2 in there, 2 squared is 4, 4 times 3 is 12, so you got a 12. 15 times 2 is 30. So you have a 12 minus 30, which is -18. -18 plus 18 is exactly 0. I feel good about that. 3 is the exact same way. And then, of course, for my math lab, they're going to want you to put your answers into bracket format. So this would be bracket 2, bracket, or 2 comma 3 bracket. That's your solution set. So that's your basic solving technique for quadratic. It's factoring and solving using the zero product property. The unfortunate part of that is this does not work every time. Not all quadratics are factorable like this. And if they're not factorable like this, you have to have a backup plan. We'll get there in a second, but that is your probably where you should start. If you're asked to solve a quadratic, try doing this method. It is the fastest thing you can do. Unfortunately, it does not work every time. All right, let's look at another one, and you'll notice they've changed the language here, and this is why it's imperative to know the similarity. In fact, that the roots and the solutions and the x-intercepts and the zeros are all the same. This is asking us for the roots. If you're not paying attention, you may attempt to do something different, when in reality you would do the exact same thing on this problem as you would the other problem. So what I'm going to do is I'm going to take my equation, and I'm going to set it equal to 0. You'll notice the other one was already set equal to 0. This one's not, so I'm going to do that myself, but that has to happen. If you're solving, one side has to be 0. That's probably something you want to know. Step 2 is to factor this thing, if possible. You'll notice that I do not have a GCF this time. All right, no GCFs here. There's nothing common to all 3 of those terms. And if you think the x is common, it's not. There's not an x in this term here. If you think the 4 is common, it's also not, because there's no 4 in this previous term, or the first term rather. So since that's the case, no GCF. Second thing to consider is a is 1 here. So the number out in front, the very first number of the standard form quadratic is 1, which indicates you can try to reverse FOIL. So that's what I'm going to try. I'm going to try to break this down just like I did the last one. The first terms here, if you do this correctly, are always going to be x. Remember, that needs to be 1 because of that. If that's some other number and you can't factor it out, you would not be able to do this. Just a heads up there. And then I'm going to follow the convention. I need two numbers rather, that multiply to 4, but add to -4. So think through that. Think of all the numbers that multiply to 4. Also, if you have a hard time thinking about this, you could just list the factors of 4. For example, you could do 1 and 4, 2 and 2, and 4 and 1. Those are the only sets of numbers that multiply to 4. And then you could figure out which one of those, and then of course you'd have negatives involved as well, but which one of these pairs could also add to, in this case, -4. And it would have to be this set right here, because if you add 1s and 4s, you get 5s, right? We don't want 5s, we want a 4 here. And then how do I get the -4? Well, I'd have to use -2, -2, right? -2 times -2 is still +4, and it also adds to -4. So if you have a hard time just doing that off the top of your head, you can always make a list and then like piece it out that way. But like I said, my two numbers are going to be -2 and -2. Now I can employ the zero product property that says if A times B is 0, that indicates that this factor would have to be 0, or inclusive, or this would be 0. And now you have two extremely simple algebra problems to solve. You solve both of these simply by adding 2 to both sides. So if you do this, the first one gives you 2, the second one gives you 2. Now, as far as your answer is concerned, you would never repeat the same number in a solution set. The only solution here is 2. It happens to appear twice. That can happen. I'll show you why here in a second. But if in general you have solutions that appear multiple times, like the same number, don't put 2, 2. It's going to count it wrong. Only list it one time. And again, if you're concerned about this, you're like, man, I don't know if I did that right. Just plug it back in. And if it equals 0, you have found the true solution. If it doesn't equal 0, go back and try it again. Figure out where you went wrong. This has got to produce a 0. This has to make this true to be your answer. That brings us to a note which specifically addresses this right here. Like, how come I get one solution sometimes? So our note says that quadratics, specifically quadratic equations, can have 0, 1, or 2 real solutions. All right, we're not talking about complex solutions at the moment. So this note's only in reference to real solutions. You could have 0, 1, or 2. Now we've already seen these two instances. We have yet to see this case here. I can draw you a small diagram that would explain when these cases would emerge. Let's say your parabola has been shifted up, or perhaps right and left and up, but it either way is sitting above the x-axis and opening up. That is an important requirement. In this case right here, if you tried to solve this, this would have 0 solutions in the real sense. And that's because solutions, if they're real, are the locations where the function crosses the x-axis. I think you'd all agree with me that this is never going to cross the x-axis. Therefore, it have 0 real solutions. If your parabola comes down and touches the x-axis and turns right there and just hits it, doesn't like pierce it or cross it, that would be an instance of 1 solution, 1 real solution that happens right there at that location. This is exactly what has happened in that previous example. This parabola, when you graphed it, it only touches the x-axis at 2, but it shows up twice because naturally there's a theorem, we'll get to it eventually, called the fundamental theorem of algebra, that says whatever the highest power is on a polynomial, that is how many solutions you have. So in order for that to be true, and you only have 1 solution, that would indicate that they both are the same. It counts as 1, but through the process, you actually get 2. They just are the same number. And then in the most general sense, normally your parabolas do stuff like that, where they do indeed cross twice. And that was like our first example where we had the 2 solutions. So just be advised that if you do only get 1, or perhaps you don't get any, that is perfectly fine. It's just dependent on where that parabola is at on the Cartesian plane. All right, so that was a pretty good discussion on how to solve by factoring. Basically, it relies heavily on your ability to factor, but that is not the only way that you can solve a quadratic. So now we're going to kind of cycle through the other ways you can do this. And some of this depends on preference, but other parts of this is going to depend on what you're given with, or what you're given to begin with. So moral of the story is you can't use these always. Some of these are very specific. All right, so let's say you don't want to use the 0 product property. Maybe we can use a different property, and this one's called the square root property. And you will find that it's very evident when you're allowed to use this process here, this property. And I'll write down some examples, and you'll probably see what I'm talking about. No hyphen here, sorry about that. Also, if the homework and or tests tell you specifically to use a certain property, that's for your own health. Like there's a reason they're telling you to do that. It's almost a hint. Don't try to buck what they're saying and do something else. Just generally try to follow the directions. It will probably be the easier method. All right, so this is a perfect example, 3x squared equals negative 27, where you would want to use the square root property. Generally, how you know that you would want to use the square root property is you're missing the b term of the quadratic. What do I mean by that? Well, look at the difference here between this example and this example. Yeah, things are on different sides of equals. You don't have the 0. That's not what I'm talking about. What I'm talking about is this one had a b term, right? It had negative 4x. We're looking for that linear x value. This one just doesn't have that. You have your a and you have your c of the quadratic. The b term is missing. If that's the case, then you can use the square root property to solve. and it will be way faster than doing factoring or any other method. Also, please be advised that the square root property, you do not need to have 0 on one side. If you do solving by factoring, you have to have 0 on one side. If you do solving by the square root property, you don't have to. This is perfectly fine. The catch there is you can only do it if you're lacking the b term. So it's got to look like this. It's got to be something squared equals a number, or something squared plus a number equals 0, or whatever the case may be. The rule is no b term. Now, the cool thing about the square root property is I could just say get x by itself. That is the equivalent of the square root property. You're going to isolate the x squared, and then you're going to take a square root. That's the square root property. In fact, we did a little bit of this last week, so this won't come as a shock to anybody, I don't imagine. So to solve for x here, step 1 would be to divide by 3. Make sure you are aware of that, though. You've got to isolate the x squared first before you do the square root. If you do the square root right now, there's no sense in you even doing these problems. All right, so make sure you're aware of that. That leaves me an x squared equals -9. And then this is where the square root property comes in. To get x by itself, I will be taking the square root of both sides of the equation. The square root of x squared is exactly x. I am inside of an equation, so I'm going to have to put a plus or minus when I take that square root. And then you're going to square root -9. And this is exactly why we learned section 3.1, is because you need to know how to take the square root of the negative here. The square root of the number 9 is exactly 3. And what happens when we square root a negative? Well, we learned last week that produces the I value. So our solutions here are plus or minus 3i. Now, as far as what we're talking about here, these are not real solutions. So what this indicates about this particular parabola is it is either above or below the x-axis, indicating it has no real solutions, but it has to have some solutions. So this is what happens in this case right here. If you get 0 real solutions, that implies that you have complex solutions. So that's the trade-off there. If your parabola is floating above the x-axis or below the x-axis and doesn't cross the x-axis at all, then you have complex solutions. And remember, they come in pairs. They have to. If you forget the plus or minus here, you're only going to have one solution, and every quadratic has 2, technically, right? 2 in this case, technically 2 in this case because it repeats itself, and then 2 in this case, they're just complex. So that plus or minus, I cannot stress that enough. That is so important to us. And then, of course, for my math lab, you would have to type that in a set like this. You would have 3i and -3i in your solution set. Let's do another one of those where we have an opportunity to use a square root. So we'll do 4 times quantity x minus 2 squared plus 1 equals 13. And again, this looks a little different, but I'm lacking a b term. I don't have number times x anywhere in here. I have this squared term, and then I have a bunch of constants floating around, which indicates I can probably utilize the square root property. Something else you could do is you could FOIL this out and then get everything on one side and try to factor it. Unfortunately, that's going to take you a lot of time. So not wrong, but probably not the most efficient way to do it. So what I'm going to do instead is move everything over to the other side and then use a square root when appropriate. That said, if I'm going to isolate the square here, step 1 would be to subtract that 1 over. Again, not to insult anyone's intelligence, but notice how I did not square root right off the bat. I'm not allowed to at this point. Some of you will try, unfortunately, but you are not allowed to until the square is isolated. So step 2 then would be to divide by 4. Get the constant over to the other side, which leaves me the quantity x minus 2 squared equals 3. Also, just a heads up here, make sure you don't fall for the freshman dream. This is not equal to x squared plus 4 or x squared minus 4. It's not anything that's remotely true, and you don't want to do that here for sure. What you want to do instead at this point is get rid of the square. How do we do so? We use the square root property, which says you can take a square root as long as you do it to both sides. So what that's going to do for you on the left is that's going to give you an x minus 2. Those neutralize each other. On the right-hand side, you took a square root, so you need to put that plus or minus in there. And then, of course, square root of 3, you're not doing anything with because that can't be simplified. And then your last step to get x by itself is to add 2 to both sides. And then something I want to make you all aware of is if you are adding 2, or anything for that matter, to a term with a plus or minus, that needs to go in front of the plus or minus. A lot of times we just add stuff on the back and it's all fine and dandy, but if there's a plus or minus involved, it has to go in the front. Has to. Make sure you're aware of that. And then, of course, you would have to put this into a set of 2 numbers, 2 plus root 3 and 2 minus root 3. You might be able to play around with that and put this all in together, just put brackets around that. I assume there's probably a plus or minus key, but knowing the program, it's probably just safer to put it in like that. And again, if you're not sure, that's the beauty of this type of math. You can check this. Just take your number, plug it in, work it out. If it equals 13, hooray, you have found the correct answer. You can check all of your answers here. It's pretty cool. All right, so that's 2 of the several methods we have to solve quadratic equations. Let's look at a third one. Which is called completing the square. This is a topic you would have learned in Algebra 2 at some point if you took that class. It's not hard. A lot of people don't like it for whatever reason. It's probably not a method you're going to use a whole lot unless it specifies you to. But what it can do for you, the reason we should probably know this is if you have a standard quadratic, kind of like the ones we did in the first set of examples, that cannot be factored, then you're in trouble, essentially. So this is a good backup plan for ones that cannot explicitly be factored. So they give you the explicit instruction that tells you how to solve. Like I said before, it's probably in your best interest to go ahead and follow their directions on that. And we'll take a look at this guy. X squared minus 6x plus 4 equals 0. And this is what I was talking about before, a little bit ago. This cannot be done using any of the methods we've talked about so far today. If you tried to do the zero product property method, you would get stopped at the factoring step. This is in standard form. It looks nice, A is 1, but when you sit down to factor it, you ask yourself, what 2 numbers multiply to 4 but add the -6, the answer is there are no two numbers that do that. So you cannot use the first method to solve this quadratic. You also can't use the second method to solve this quadratic, the square root property, because you have a b term here. You have a b involved, which is not going to be able to be done with a root, at least as it is now. So at this particular moment, you're in trouble. So you've got to have a backup plan, and that's where completing the square comes in. There's also another method that could get you out of this that you may like better, but this is something you should definitely know. All right, so here's how this is going to work. And this is very procedural, so please pay close attention to this if you don't know how to do this already. What you want to do is you want to get rid of this number right here. This is the number that's screwing everything up. So what I'm going to do is I'm going to move that to the other side. And you're going to leave a space there because we're going to replace this number with a better number. So how do we get that 4 to the other side? Well, we would subtract it over there. And then again, I'm going to leave that space open. So that's step 1 of completing the square. If you know it's not factorable, or if it says to complete the square, step 1 is to go ahead and move that over. And this is assuming a is 1. If that number's not 1, we have to do something different. We'll get there in a second, though. Step 2 is to put a better number in there. Now, how do we know what the better number is? Well, there's a tiny little formula for you that will tell you what the better number is. To figure out that number you put in there, you use this formula right here. You take b, whatever b happens to be in this, you half it, and then you square it. That is how you find the number when you complete the square. Half of b squared. As far as this list that's kind of growing of things you just need to know, that's going to be on there, along with the slope formula, how to find the vertex of a parabola formula, all of that stuff. Just, it has to be built in. There's no one going to be there to hand that to you when you need it. So to fill in this gap here, I'm going to half b, so half of -6, which is -3, and then I'm going to square it. -6 over 2 squared is 9. So I'm going to put a positive 9 in that gap. Half of b squared, that's how you get that number. Now, can I do that mathematically? No, absolutely not. You are not allowed to take an equation and just slap a 9 on one side of it. So to make this okay, I also need to add a 9 to the other side. That is the only way I can get away with doing what I just did there. I've got to keep my equation balanced if you want to take it back to like early algebra. And that's pretty much it as far as completing the square, because look at what you've done now. If I asked you to factor this, before you couldn't do it, but now you are guaranteed to be able to. In fact, if I factor this side here, and I ask you what two numbers multiply to 9 but add to -6, those two numbers are guaranteed to exist. If you did this correctly, you will always have two numbers that do that. And in fact, what are those two numbers? Well, those two numbers would be -3 and -3. So again, if you can't factor, take this number, move it to the other side, do half of b squared and put that in that gap there, and by default, you're going to be able to factor that now. On the right-hand side, you're just going to clean up whatever it says. What is -4 plus 5 or plus 9? Well, that's 5. So I'm going to clean that up. Now, once you're here, here's what you cannot do. Some of you, regardless of how many times I tell you not to, will say, oh, cool, x minus 3 equals 5 and x minus 3 equals 5. And you'll set them both equal to 5 and then you'll solve. Unfortunately, and I wish we were in class because I'm sure someone could explain to me why we can't do this, that property that we're using to do that on the other problems is not called the 5 product property. It's called the 0 product property. So if you feel like you should ever set two factors equal to a number, that is not allowed ever unless that number is 0. All right, so make sure you're aware of that. Here's what I'm going to do instead. If I have x minus 3, I can rewrite that as x minus 3 squared. That is the literal combination of x minus 3 times x minus 3 is x minus 3 squared. And that still equals 5. And this is why this process is called completing the square, because you took some jank quadratic here, and what did you turn it into? You turned it into a square. You completed it. Now, what happens when you have a square? Well, now you are directly back up here into this process. If you have a square and no b term, which is exactly what's going on here, you're going to use the square root property. So completing the square is essentially just a method to take some crappy things and to turn it into the square root property, which is actually one of the easier ways to do a problem. So what do? I'm going to now square root both sides. That leaves me x minus 3 on the left. On the right, I'm going to have to put a plus or minus because I'm inside of an equation and I just employed the square root. And then, of course, square root of 5 is one of those deals where you're not going to be able to break that down any further because 5 is prime. And then finally, you're going to get x by itself. You're going to add 3 to both sides. And as I said in the last problem, if there is a plus or minus involved, whatever you add or subtract over has to go in front of the plus or minus. If you put it in the back, you're going to have 2 wrong answers instead of 2 right answers. So be careful with that. Of course, with MyMathLab, you would want to put these into brackets, into a set like this. Also, again, if you're concerned and you're like, man, I don't know if I did that right, plug it back into the original. If you put 3 plus root 5 in here, of course, your calculator can help you with that, and it equals 0, then you've found the right answer. If it doesn't, you've either plugged it in wrong or you have the wrong number. So in theory, when solving quadratics, you should really never have the wrong answer. If you have ample time and ample ability, you should always get the right answer to submit. Granted, you, again, know the content. You should be able to check and fix it, that type of thing. And as I change pages here, we'll do part B of completing the square, so you can see that one more time. And we'll actually do this where it's not ready to go to begin with. (4x squared plus 8x minus 1). All right off the bat, this is another instance of if you try to use the other techniques, you're in huge trouble because it's not going to work. Can't use the zero product property because this is not factorable in the normal sense. I can't GCF this, can't pull a 4 out of each of these. That means I can't do the reverse FOIL thing, which means I can't set them equal to 0. So first method, out. Second method is out immediately because I have this b term. I can't use the square root property at the moment. What does that mean for me? It means I need to probably try something else, such as completing the square. Now, please be advised that you cannot use completing the square if a is not 1. You cannot do it. Okay? Make sure you hear me out on that. If you need to jot that down in your notes, great, do it. You cannot complete the square if a is not 1. That said, if a is not 1, that doesn't mean you can't do anything, because you have the power to turn that into a 1. In fact, how do you turn 4 into the 1 or into a 1? You just divide it by 4. So, moral of the story is if the zero product property doesn't work and the root property is not even applicable to the problem, and you want to complete the square and a is not 1, fix it. You have the ability to do so by dividing the whole equation by whatever number is currently a. So I have 4x squared divided by 4, which is just x squared. Hooray, a is now 1. But the cost of doing that is you have to divide all of the equation, the entire thing, by 4. So make sure you do your due diligence and do it all. So I also have 8x over 4, which is just 2x. And then I have negative 1 over 4, which is negative 1/4. And then I have 0 over 4, which of course is 0. This is the same equation. Yes, it looks different, but it is for all mathematical purposes the same. simply because I divided by 4 on both sides. So whatever note you need to make to yourself, that's why we did that. If a is not 1 and you would like to complete the square, you need to fix it by dividing. Step 2 is to check on the off chance that you already have a square. How do you know? Well, you would need 2 numbers that multiply to negative 1/4 and add to 2. And I think you can all agree with me that does not exist. And if it does, it's nothing I can think about relatively easily. 2 numbers that multiply to a negative 1/4 and add a positive 2. I can't think of what they are. So I need to move this guy then. This is the problem spot. We're going to move him to the other side. And we move negative 1/4 by adding it. So now I have a positive 1/4 over on that side. And remember to leave yourself a space because you're moving that deliberately to put a better number in there. And then right in that gap, that's where you actually do the completing the square formula. I'll remind you again, it's half of b squared. And our problem now, our b used to be 8, but remember we forced it. Now our b is 2. If we half 2, we get 1, and 1 squared is still 1. So I'm going to put a plus 1 in that gap. And then to keep our equation balanced, we have to make sure we add 1 on the right-hand side as well. If you've done this correctly, you should now be able to factor the left-hand side, and in fact, those 2 factors are going to match. I need 2 numbers that multiply to 1, but add to 2. What are those 2 numbers? They are 1 and 1, right? 1 times 1 is 1, 1 plus 1 is 2. Multiplies to C, adds to B. On the right-hand side, you feel free to clean that up. You have 1/4 plus 1, which is not 2/4. I don't want to get too involved in the fractions at the moment, but 1/4 plus 1 is 5/4. Make sure you use common denominators there. And then, since those are the same factor, you can rewrite them as x plus 1 quantity squared equals 5/4. And this is what I was talking about with completing the square. It's very formulaic. It's got the same steps. Some of them may have extra steps at the beginning, but once you get down to this level here, it is very, very repetitive. That number goes over, you do half of b squared, you add it to both sides, and then you're going to have a square here, and then some random number here. This is exactly how it goes every time. And that's the beauty of it, is because if you do that correctly, you're now into the square root property territory where all you need to do is square root both sides. The square root of x plus 1 squared is just x plus 1. I took a square root inside of an equation, so I need the plus or minus. And then you have the square root of a fraction here. So please be advised that if you square root a fraction, we'll jot this down. It's been a couple of days since we've talked about this, but the square root of a over b is the square root of a over the square root of b. To square root a fraction, mainly what I'm saying there is you just square root the top and you square root the bottom. I cannot simplify the square root of 5, but I can simplify the square root of 4. So this becomes the square root of 5 over 2. So be advised, if you can square root the top or bottom, you need to do so. And then that brings us to our last step of getting x by itself. To do that, all I need to do is subtract 1 from both sides. And remember, when a plus or minus is involved, you're going to put that minus 1 in this case in front of the plus or minus. So you get this set of answers, -1 plus or minus the square root of 5 over 2. And then, of course, put it in your solution set. Generally, after I went through the tests, be careful with this, folks. Some of you have the right answers, but you put like an extra space in a certain spot and the program counts you wrong. Just be very deliberate as you put those things in. I'll, of course, go back and look. I look at all wrong answers just to see if you put in something correct that the program counted wrong, and I'll fix them. But just in general, if you catch those ahead of time, it will not only make my life easier, it'll make your score look better when you're done. So for mental health purposes, just be very careful. All right, so those are 3 methods of solving. We have another major one, a 4th one, and then we're going to get into the inequality stuff, which relies on all of this, and some other topics at the end of this. Like I said, this is a pretty long section. I do want to take a brief break for a moment. At 10:03, in 5 minutes from now, we will resume with our 4th method. Just go ahead and take a quick break. All right, folks, it's 10:03. We're back here. As I was sitting there thinking, I remembered something that a lot of you guys missed on the test. I just wanted to clear up what it means to be constant as far as a function is concerned. In order for a function to be considered constant, it means it doesn't change. Like it's literally the same value at all times. So only functions that are horizontal lines are considered constant. You may have functions that are constant at certain locations, but in order to be typical or generally called a constant, it cannot change. Some of you were saying that functions like this were constant. These functions have a constant slope, but they're not by definition constant because they're changing. So please make sure you understand the difference. I think something got crossed up there for some of you. Other than that, there are other mistakes that happen. Again, if you have any questions, if you go through the test and see what you got wrong, or in general, like you know for a fact you got something wrong, please ask me, especially before the final, so we can get those cleared up. That said, we are ready for our 4th and final general solving technique for quadratics. This one, for some students, they will use this for everything because this is the one method that works on all types of quadratics. No matter what the quadratic is, this method works. It is also the most tedious method. So for those people that like efficiency, they're probably going to learn those other 3 that we just talked about and learn them very well so they can use those instead. But for everybody, if there is some quadratic that for whatever reason you cannot use the other 3 methods for, or it's specifically telling you to use this method, this is your grand backup plan, and it's called the quadratic formula. And while we're here, we're also going to talk about this other concept that relates to the quadratic formula called the discriminant. Now, I would venture to guess that most of you already know the quadratic formula. I hope, in fact, you do. I worked with a lady back early in my career that said if students leave Algebra 2 and are unable to recite the quadratic formula for the rest of their lives, they have failed as a teacher. So I don't know who you had for your pre-college algebra career, but hopefully they instilled this formula in you because it is incredibly important. And if they haven't, then you need to go learn this immediately. So what the formula says on a standard quadratic, so you need it to be looking like this right here. So standard form, you have an A, you have a B, and a C, or this form up here, A, B, C. The formula says, in order to find your solution, X, it is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. And just like in Algebra 1, just like in Algebra 2, just like in any other algebra class, you need to know this formula. Hardcore, you definitely need to know this. So if you already know it, great, you're ahead of the curve. If you're sitting there being like, I've never seen this before, or I kind of remember that, learn it. Make sure you know it. There's a bunch of songs that exist to help you remember that. The main one, I think most people know, it goes to the tune of Pop Goes the Weasel. that little weird song. I'm not going to do it, but you guys have YouTube. Type in quadratic formula song. There are a bunch of versions. There's like one that goes to the tune of Work by Rihanna, I think wrote that song. I don't know, there's a bunch of them, but whatever you need to do, learn that. And importantly, within the quadratic formula is this concept known as the discriminant. The discriminant specifically is just the b squared minus 4ac portion of the quadratic formula. So discriminant is that term, b squared minus 4ac. And aside from the quadratic formula solving quadratics for you, this right here, the b squared minus 4ac, the discriminant, will tell you what your solutions look like before even doing the problem, which is useful because some of these questions that you could get, instead of asking you what are the solutions, it may ask you what type of solutions do you have, meaning are they real or are they complex? Also, it tells you how many you're going to have. So quickly on the side here, if your discriminant, b squared minus 4ac, is positive, as in you took the a and the b and the c from your quadratic and plugged it into this little formula, what that indicates is your answers are going to be real, and you're going to have two of them. Okay, so if the discriminant, if b squared minus 4ac, just that little part of it, aka the inside of the square root here, if that is a positive value, you know you're going to have two real answers when you get done solving it, if you were to go ahead and solve it. If the discriminant is equal to 0, that tells you that you are going to have one real solution. Now, in reality, you actually have two there, but that was the case where they're both the same number. That's how that happens. If this inside stuff equals 0, you're going to get a real solution, but they're going to repeat themselves. It's going to count as one unique solution. And then if your discriminant, if b squared minus 4ac happens to be negative, that's where you cross over into the complex solutions. You're going to get two answers that have i's in them. And like I said, make sure you know this. Most of the time, you just need to solve it. In fact, if it asked you how many and what type of solutions you have, you could just solve it and look at them and then answer that way. But as far as efficiency is concerned, knowing this little formula, which by the way, you should already know because of the formula itself, and knowing its pairing with 0, is it more than 0, less than 0, or equal to 0, that can answer those questions rather quickly. Again, it doesn't tell you what the solutions are, but it tells you what they look like or what they would be, two real, one real, or two complex. So a lot of good information here. Make sure you know this set of facts and the formula at the base level. Make sure you know this formula here. It will answer all of these questions. If you get yourself into trouble, this works on all of them. It is incredibly nice that there's a unified formula for quadratics. And we'll do a couple examples of this as well. And like I said before, if it tells you specifically how to do or to do a problem using a certain method, make sure to do so. But this is going to say using the quadratic formula. And every once in a while, they will give you quadratics that do not look like any normal quadratic. Like, this is so far from standard form. And that's not a big deal. Just be advised, kind of like some of the other stuff we were dealing with, you have to get it ready to go before you try to use any of the methods. So if it doesn't look like a normal quadratic, don't fret, just fix it. For example, to fix this guy, we need an x squared term. We get that by distributing here. So I'm going to rewrite this as x squared minus 3x. And then also to be in standard form, we need all of the terms to be on the same side. So to do that, I'm going to need to subtract the 4x over. which gives us a standard form quadratic of x squared minus 7x plus 6 equals 0. So occasionally there will be a little work to do before getting started, but if you're aiming to use the quadratic formula or to use the first method, the solving by the zero product property, you've got to get it in standard form to begin with. Now, this is going to be a bummer, but you could factor this. This one's factorable. You could use the first method here. Two numbers that multiply to 6 and add to -7, those numbers exist. You could set up the factors and set them equal to 0. However, this does not ask us to do this by using the zero product property. It says use the quadratic formula. So I'm going to neglect the easy, efficient method and do the tedious method, the quadratic formula. But again, that's kind of the whole point of this example. So flipping pages here. We are going to be using the quadratic formula. I'll write it down again. On x squared minus 7x plus 6 equals 0. And it is legitimately a formula. You're going to take A, which is 1, B, which is -7, C, which is 6, and you are going to plug it in to the formula itself. So it starts off with -b. Our B is -7. So -7 is, of course, 7, plus or minus the square root of B, which is -7 squared. Notice how I use parentheses there. That's incredibly important. Minus 4 times A, well, A is 1, times C, C is 6, all over 2 times A. And then if you clean this up very carefully, it will give you the two answers, guaranteed every time. This is a very cool formula. Yes, this is sort of tedious, but the fact that it will just spit out the answers regardless of whether they're real or complex or whatever, that's a powerful thing. Let's start inside the root. Let's clean this up. I have -7 squared, which we know is 49. And then I have 4 times 1 times 6, which we know is 24. So I have 49 minus 24, which is equal to 25. This, by the way, if it were to ask you and say, what is the discriminant? That's what 25 is in this problem. 25 is the discriminant. And that tells us something that's going to happen. Since the discriminant is 25 and 25 is more than 0, I know when I'm done with this problem, I need to have 2 real solutions. That's a good check as well. If I got like a complex answer somehow, I know I would have done this incorrectly. And then, of course, that's over 2. I will tell you the number one mistake students make is they forget the over 2a part. So make sure you have that in your answer. Cleaning this up further, if you are able to take the square root, please do so. I know that the square root of 25 is, of course, 5. And then at this point, this is going to branch off into 2 different answers. You have the positive answer, and then the answer that comes from the adding, and the answer that comes from the subtracting. So I do 7 plus 5, which is 12 over 2. 12 over 2 is 6, so that's one of my answers. And then I do 7 minus 5, which of course is 2 over 2, which gives me 1. So those end up being my 2 solutions, 6 and 1. And just like all the other problems, if you're concerned about those, feel free to plug them back in if they give you zeros in the original, or you can go back to even the first one they gave you. If it's true statement, then you have the correct answers. And again, this formula works on any of them. As long as you can get them into standard form, you can use this formula. It is a great thing to know. It's a great essential backup plan for problems if you aren't able to use the other methods. Want to do one more just to cover the bases here. We're doing 2 of each. Let's look at 2x squared minus x plus 4. And again, if you kind of cycle through the other methods, zero product property is not going to work because you have a 2 out in front. The square root method doesn't even apply here because you have a b term. You could complete the square. You could half all of these numbers and then move that over and fill in the gap. That's perfectly acceptable. Or you could just use the quadratic formula, which is exactly what we're going to do here. So let's start off. We have x equals negative b. Please be advised that b is -1 here. So we're going to start off with a positive 1. Negative 1 is 1, plus or minus the square root of of b squared, which is -1. Again, using parentheses, minus 4 times a, which is 2, times c, which is 4, all over 2a. We start our simplification inside the root. Please be very, very careful here. We have -1 squared, which of course is just the number 1. And then we have 4 times 2 times 4, which is 32. So we end up doing a 1 minus 32, which is a -31. Again, if they're like, what's the discriminant? Your discriminant value is -31. And that's your b squared minus 4ac. Also, please be advised, since the discriminant is negative this time, our 2 final answers are going to be both complex. We're going to have 2 complex answers at the end of this because the discriminant is negative. Next step is to simplify the root, if at all possible. Hopefully you would agree with me. You can't really simplify this, at least the number. The number is going to stay in there because 31 is prime. You can't break 31 down, and you can't take the square root of it. But you can square root of -1. We learned last week that the square root of -1 is I, and this is what makes this all okay. The discriminant told me I was going to have complex answers. That's exactly what happens when you take a square root of a negative. You get a complex result. And of course, that's sitting over 4. And then if you recall, when we were talking about complex numbers last week, I said I would like you to write those in standard form, which there were 2 parts. There was a real part, and then there's the complex part. And to do that, all we did was divide both of these by 4. So this becomes 1/4 plus or minus the square root of 31/4 I. That puts you into standard form, and I prefer you do that. And it's highly likely the online program requires it in that form as well. Just be careful, play around with that. I doubt it would take that. It probably wants the standard form. And then, of course, you would enter that in set notation. Just like this. Also, when the complex solutions pop up, you can still check these. It's going to take a bit more work to do, but you can still plug those in and check to see whether it equals 0. Like I said, pretty involved, but it's still possible. You can always check your answers when you're solving quadratics, regardless of what they look like. All right, so that concludes basically the first bulk of this section, all of the solving techniques. There are 4 of them. This would be a good point if you have any questions over any of the 4 techniques or anything you've seen so far to go ahead and ask. And if there aren't any, we'll go ahead and switch over to inequalities. All right, so quadratic inequalities. Anytime you are solving inequalities, you should prepare yourself for infinitely many answers instead of like two solutions or one repeated solution or two complex solutions. We're talking about large swaths of the x-axis. So you're going to get interval answers like, oh, my answers are between 2 and 35 or something to that effect. And that's because if you look at an inequality with a quadratic, so we're talking parabolas here, and instead of saying, okay, where does the parabola equal 0, which would be these locations, we could instead ask, when is the parabola less than 0? When is the quadratic below the x-axis? And you can see here, the quadratic is below the x-axis all through this section. And how many numbers are in between these two? Infinitely many. And this is where the interval notation comes together. Or instead of asking you where is the parabola below the x-axis, I could say, when is your quadratic greater than 0? When is it above? And, well, it's above on this side. It's also above on this side. So there you get infinitely many different answers as well, but you're into two different sets. So you're either going to have ones that are like 2 to 6, or you could have negative infinity to blah, union blah to infinity. So there's two types of setups here, depending on whether you want to be above or below the number in question. And the cool thing about this, while this may seem more convoluted, you're basically just going to solve the quadratic and then just do a little diagram like this to figure out what intervals you need to answer, or I can show you how to do it through a table, which is probably even easier. But the main part of quadratic inequalities is exactly what we've been doing today. It is exactly the same. You need at a minimum to find where it crosses the x-axis. And if it doesn't cross the x-axis, then you're going to have really easy answers. For example, when is that quadratic greater than 0? All of the time. When is it below 0? None of the time. So in order to do this meaningfully, finding those solutions, if they exist, is going to be the number one priority for quadratic inequalities. So let's start with this one. Let's solve when is x squared minus x minus 12. Instead of being equal to 0, let's find out on the interval that it is less than 0. The first thing you're going to do is you're going to temporarily ignore the fact that it's an inequality. All right, you got to be careful doing this because sometimes kids do this first step and then they forget to go back and finish the problem. But for the moment, what you need to do is figure out, where does this thing cross the x-axis? Does it cross at all? Those are the types of questions, those are the types of things we need to figure out before we can even talk about intervals. So I'm going to solve this just straight up like we would have done in the last part of today's lesson. And you can use any of the methods you want as long as they're applicable. If you would like to use the quadratic formula, go for it. If you would like to complete the square by moving the 12 over and then filling the gap in with the correct number, go for it. But what I'm going to try always, if possible, is to use the zero product property. I'm going to try to factor this because it's way, way faster than doing those other methods. So to do this, I'm going to be looking for two numbers that multiply to C, negative 12, but also add to B, negative 1. So I need you to think about that. Are there two numbers that multiply to negative 12, yet add to negative 1? Yes, in the chat. Good job, Logan. They are indeed negative 4 and 3. Negative 4 times 3 is negative 12. Negative 4 plus 3 is negative 1. So I'm going to put those in there. Negative 4 and positive 3. And then, again, these are my factors. I don't want factors. I want solutions. So I'm going to use the zero product property. This would have to equal 0, or that one would have to equal 0. I just set them both equal to 0, and that's going to give me my two solutions. add 4 to both sides on the left one. So x equals 4 is a solution. Subtract 3 from both sides, which tells me -3 is also a solution. Now, this is where you got to switch back into inequality mode. These are not your answers. All right, these are the endpoints of your intervals for your answer. Now, here's what you should do instead. You can draw a picture of this. That would be one way to do it. We learned last week how to draw a quadratic. And what's going to happen with this quadratic is it's going to pass through 4 and -3. You also know that it opens up. So, because a is 1. So you could quickly sketch this guy. And I don't know much about this. You could find the vertex. You can do whatever. But generally, you know it opens up and it goes through those 2 points. So if I want to know when does the quadratic, when is it below 0? When is it less than 0? I can look at this graph, this quick little sketch I drew, and figure out that it is below 0 in between the 2 x-intercepts. Okay, so it's below 0 in between the 2 x-intercepts, not on the outside of the intercepts. So that's one way to do it. Now, if you know you are not very strong with the graphing component of this, I would encourage you to get strong at it because you're going to be tested over it eventually. But something else you can do, and this is what a lot of students end up doing, is they do it through a table. And as far as this being pre-calculus, this is a good thing to know how to do as well. What you want to do is you want to divide up the real number line, negative infinity to positive infinity, at these numbers here. So the first division, the first subset would be from negative infinity up to -3. Then you go from -3 up to 4, and then the third interval is 4 to infinity. All right, those are all the 3 intervals where your parabola could either be above or below the x-axis. Then what you want to do in your table is pick a value in each of those intervals. Okay, don't pick the endpoint, but pick the value inside of it. For example, a number in between negative infinity and -3. For example, you could use -4. You could use -18. You could use -1,000. It doesn't matter. Just make sure it's in that interval. Same thing with this. If you have an interval, by the way, that straddles 0, 0 is the best number ever to plug in, which is your end goal here. So I'm going to pick 0 out of this interval, and then I'm probably going to pick 5 out of the top interval. So again, you find your solutions, and then you use them to break up the real number line at those points. 2 x-intercepts gives you 3 intervals, and then pick a test value from each one. And then what you're going to do is you're going to plug it in. Whatever value you pick, you're going to plug it into the inequality. And there's 2 things that could happen. It's either going to be a true statement or it's going to be a false statement. For example, let's plug -4 in there. -4 squared is 16. 16 minus -4 is 20. 20 minus 12 is 8. Is 8 less than 0? No, it is not. That is a false statement. Plug 0 in. 0 squared is 0. 0 minus 0 is 0. 0 minus 12 is -12. Is -12 less than 0? Yes, it is. That is a true statement, which means, by the way, that all of the numbers in between these, every number in that interval, also is true in that equation, that inequality up there. And then make sure to check them all. You're going to put 5 in here. 5 squared is 25. 25 minus 5 is 20. 20 minus 12 is also 8. Is 8 less than 0? No, it is not. And right here, this tells you your answer. It says this inequality is less than 0. This parabola is less than 0 only on the true intervals, only on the interval from -3 to 4, which is exactly what I knew from my picture, right? When is the parabola below 0? It is on the interval from -3 to 4. This also will tell you, again, if you're bad at sketching, if you're bad at graphing, this table does not require a graph. It requires you dividing up the interval, picking a test value, and then plugging it in to figure out whether it's true or false. But either way, end of the day, my solution here is -3, 4, And then also, just a heads up here, I'm going to use these open parentheses because this is a strict inequality. Make sure you're aware of that. Strict inequality means you don't actually get those numbers. You would have basically a missing spot there, a hole. So inequality, open brackets, strict inequality, open brackets like this. That's your answer. I want to do another one of those that obviously does something a little different that wouldn't necessarily be in between here. Let's see what happens when it's somewhere else. So let's look at this one. Solve 2x squared greater than or equal to negative 5x plus 12. Right off the bat, regardless of whether this is an equality or an inequality, this is not remotely in any shape to solve it. So we need to fix this essentially. And this is what I've been talking about through this whole lesson. If you know it's going to be something standard form like, and you know that you're going to try to factor it or use the quadratic formula or whatever, make sure you get this ready to go, as in get everything on one side unless you are doing the square root property, which is not even applicable here. So I'm going to move this stuff. I'm going to add the 5x over to the left, and then I'm going to subtract the 12 over there as well. So now that this is this parabola is greater than or equal to 0. When you do inequalities, you want a 0 there. When you're solving, most of the time you want a 0 there, just to be completely upfront with you. At this point, you're going to pretend for a moment that that's an equal sign. And just like we did up here, you're going to find your two solutions. Unfortunately, A is not 1. So you are not going to be able to do this zero product property like we did in the last example. So we need another method. You could divide this whole thing by 2 and then complete the square. I would not advise that because B is going to become 5/2, and then you're going to half it again and square it. Probably not worth your time. So instead, I'm going to find the solutions using the quadratic formula. Just got a question in the chat. Does the 0 always have to be on the right side? No, it does not. If you flip this around and the 0 is on the left, it's fine as long as your inequality is pointing in the right direction. So it does not matter. I am very systematic in my mathematics. I always try to get the 0 on the right, but if you're not that person, as long as everything is legitimate, you're fine. As I was saying, though, this is going to require the quadratic formula. That's probably the easiest, most direct route to get to the solutions, which is the first step of finding the interval where, in this case, the parabola is above the 0. So again, just a quick sketch. I don't know what my answers are yet, but this is a parabola, a skinny parabola that opens up, and I want to know when is it above 0. That's what I'm looking for. So using the quadratic formula, we're going to do the opposite of b, negative b, which is negative 5, plus or minus the square root of b squared. So 5 squared minus 4 times 2 times negative 12 all over 2 times 2. Let's clean up the stuff inside here, the discriminant. This is going to be a 25. This, we're going to have to watch out here. We have a couple negatives going on here. But either way, we're going to do 4 times 2 times 12, which would be 8 times 12, or 8 times negative 12. So this ends up being a negative 96. All right, so being careful here, this would be 25 minus negative 96. 25 minus negative 96. So these double negatives make a positive, which makes this 25 plus 96, which is 121 all over 4. So watch out for that, students, if you're doing the simplification of the quadratic formula. If you have minus and then a negative, you're going to be adding those two terms together. If you have a minus, negative, negative, then you're going to be subtracting the two terms. You got to watch, count the negatives, and pay attention to that. Conveniently, though, this didn't have to be so nice, but it is. The square root of 121 is a perfect square. You get 11 out of that, which doesn't always happen, but when it does, that's really nice. And then that's going to split you off into your two solutions. So we have -5 plus 11, which of course gives us 6, and we have 6 over 4, which simplifies down to 3 over 2, 3/2. And then we have -5 minus 11, which is -16 divided by 4, which of course is -4. So those are my two solutions. And then again, you could, if you know what you're doing as far as a sketch of a parabola is concerned, you could figure out the answer from that. I'm going to go back to this table because, I mean, this is pre-calc. You will need to know how to do tables eventually. And you're going to divide up your interval based on those two solutions. So the number line starts at -infinity, and your parabola is moving, and then it crosses the x-axis at -4. Make sure you do the lower one first. Also, you have equality here, which means these are legitimate answers that work inside of this inequality. All right, so we're gonna have to watch our in signs here, whether we use a parenthesis or a square bracket. For now, tentatively, I'm gonna use a parenthesis because I can't put a square bracket on both of them, but I'll clarify this at the end. But for now, for this table, I'm just gonna use parentheses. After it crosses the x-axis, it continues doing whatever, and then it crosses the x-axis again at 3/2. Notice how I went from the smaller one to the bigger one, and then from 3/2 to infinity, it continues going in some direction. Step 2, once I have that broken up, I'm going to pick a test value. I dropped a negative here. That should be a -4 in there. And I don't want to get too far away from -4. I think probably the smartest answer or smartest number to pick here would be -5. Feel free to do something more extreme if you want. Just make sure for a fact it's inside that interval. This is the interval that straddles 0, so I'm going to pick 0. If you'd rather use 1 or -1 or whatever, feel free. And then this interval here, 3/2 to infinity. You could pick 2 if you wanted. 2 is the next whole number after 3/2, or you can pick something larger. Either way, just make sure for a fact it's in that interval. And then again, what you're going to do with this is you're going to plug these in to your inequality. And you can use either one, actually. If you'd rather use the original, that's fine. It's probably easier to think about in terms of the one compared with 0. So that's what I'm going to do. I'm going to plug this in. -5 squared is 25, and 25 times 2 is 50. 5 times -5 is -25. 50 plus -25 is 25, and 25 minus 12 is 13. Is 13 greater than or equal to 0? Yes, it is. So that's a true interval. Next, I'm going to do 0. 0 squared is 0. 2 times 0 is 0. 5 times 0 is 0. 0 plus 0 minus 12 is -12. Is -12 more or equal to 0? Most definitely not. So that's a false interval. And then I'm going to finish this up by doing 2. 2 squared is 4. 4 times 2 is 8. 2 times 5 is 10. 8 plus 10 is 18. Minus 12 is 6. Is 6 more than 0? Yes, it is. So you'll see we have two intervals at which we have legitimate solutions that validate the inequality here. And we knew this going into it. This little sketch I did, if we want to be greater than 0, you see we're greater than 0 on this side, and greater than 0 on this side, which means this whole axis is good and this side of the axis is good. It's actually the middle part that's bad, because those are the ones that are less than 0, like we had up here in this previous example. So let's write our answers then, and this is where we work in the fact that this is equal. If this is the case, if you have equality, whatever your answers are where you're going to put those square brackets. So I'm going to turn this one, so this used to be negative infinity to -4 parenthesis. I'm going to turn that into that square bracket, because these are legitimate solutions. I just didn't want to put square brackets everywhere, because then I have a false table. But make sure in your answer, if you have equality, you use a square bracket on the number or numbers. If you do not have equality, you're going to use parentheses on your intervals. And then, of course, it's not just this interval. I was also true over here. So I'm going to union that with square bracket again, because I have equality, 3/2, and then infinity. And remember, infinity always gets the parenthesis because you can't contain it. It's a concept, not a number. Also, I noticed some of you guys are absolutely awesome on the test, and you use the union symbol, and it counted you wrong, because instead of it asking you to give it in this format, which I think is silly because this is the absolute correct format, it just asks you to list the intervals. So it wanted a comma in between. I personally don't care. Like I said, will go back and fix this for you, but if it says specifically on what intervals is this true, it's probably looking for them separated with a comma, when in reality, this is the correct answer. If you're like, wow, that counted me wrong, and he said I could do that, be aware I will always go back and fix that for you on tests, so you don't have to worry about that. But just, again, read the instructions, just be careful on what it's asking for. It could ask for either, hypothetically. But that's how that works, folks. Please, before we change to our last topic, make sure you're aware of what this requires. Please practice this. It is identical to what we've been doing all day, with the addition of either a little sketch or a little table to figure out where are those infinitely many different answers. On what interval is this true? On what interval is the parabola below or above the x-axis? It won't just be two numbers. It'll be a whole set of numbers. Make sure you understand the difference. And if there are no questions over inequalities, we will switch gears one more time and cover the last topic of 3.3. All right, so at the end of this section, we swing back around and we do something we've already done in this class. In fact, the second question, I think, on your test that all of you took was a question that gave you this crazy formula. It wasn't even that crazy. It gave you a formula, and it said, please solve for H, or please solve for K, or please solve for T. And it just had a bunch of variables in it. And it was just a check of how strong are you at basic algebra. How are you able to get that variable by itself? Well, in this section and in this chapter 3, this comes back around. So you're going to get a second chance at this. However, this time, instead of it all being linear, you may have a quadratic term or variable to a second power, or something that would require you to utilize a root to isolate a variable. So same general concept, just a little more complicated. So I'm going to do a couple examples with you to show you how this works. And I would encourage you all to obviously practice this when you get to this part on the homework. So the instruction will be the same as it was in the previous chapter 2, when we did this last. It's going to ask you to solve for the variable. It will give you a little equation or a formula, and then the variable that you'll need to solve for. In part A, we'll start with a very basic formula that all of you should be aware of. A equals pi r squared. And I want us to solve this for r. Can anyone in the chat tell me what this formula is? Someone has to know. Very good. It is indeed the area formula for a circle. Great job. Okay, so yeah, that's exactly. We're dealing with pi, radius squared. This is the radius of a circle. If you plug that in there, that gives you the area of said circle. Not the point of this. The point is to get the radius by itself, aka find the formula. If you know the area of a circle, that would give you the radius. Step one, just like it was in the last chapter, is to isolate the variable you are trying to solve for. That's going to require me right off the bat to move the pi. Since pi is being multiplied, I'm going to need to divide that to the other side, which leaves me r squared equals area over pi. And then this is where the quote unquote new stuff comes in. How do we get r by itself now? Well, it's squared, so how do we undo a square? We're going to use a square root of both sides. The square root of r squared is just r, which is exactly what we want. We are inside of an equation here, so you're going to want to throw that plus or minus on the right-hand side. And then since I don't know what the area is, and since square rooting pi would be a nightmare, I'm just going to leave it just like this. So that's your simplified formula for the radius. So no different than what you were doing before. It's just now you have the opportunity to use a root. That is the only difference between what we were doing in the last sections, last chapters rather, and today. I'm going to try one more of these. Let's look at this formula. Volume equals one-third pi r squared h. Yes, Logan, I just saw your comment. The square root of an irrational number sounds ugly. It is incredibly ugly. Very, very astute observation. That would be just an absolutely gross number there. Part B, one-third pi r squared h. Again, I'm going to open this up for you guys to show me your knowledge. What formula is that? I already told you it's a volume formula. What is this the volume of? It's a good guess. It's not a cylinder. This is a cylinder. What happens when I toss the 1/3 out there? What do you guys think? What's this the volume of? What is 1/3 of a cylinder? There you go. Yep, very good, Hannah. It is a cone. You were looking at the volume formula of a cone. This class would not require you necessarily to know your basic formulas like this, but if you guys have any plans on going further in math, like to calculus, this is the kind of stuff you just need to know. So it's not bad to review this for sure. But yeah, this is a cone. And I'm glad this one came up because the one on the test, for some of you, probably all of you, had a fraction involved, and some of you got it wrong because you did not know how to mess with this fraction. So let's start there. Actually, let me tell you what we're doing. We're going to solve this one for r as well. And to do so, I need to at least get the r squared by itself, and then I can use the root. The first thing you need to deal with, though, is this 1/3. And I saw a lot of you guys in the work you submitted divide both sides by 1/3 or whatever number it was on the test. That is not how you move a fraction to the other side. You don't divide by the fraction. So here's our second stab at this. To move the 1/3 to the other side, instead of dividing by a third, we're going to multiply both sides by the reciprocal. I'm going to multiply both sides by 3 in order to move the fraction. So we don't divide by fractions, we multiply by a reciprocal. So make sure you're aware of that. So that turns into 3 volume equals pi r squared h. That's your first step of getting r by itself. Step 2 is to move basically everything else. You want to get the r squared by itself, like I said before. So I need to move the pi and the h. And since pi and h are being multiplied to the r squared, I'm going to move it by dividing. And in fact, I can just do that together. There's no reason I need to do that separately. So I'm going to divide both sides by both pi and h at the same time, since they're all being multiplied at the same time. So cancel, cancel. Those are now gone. I'm left with r squared, and that's equal to 3v over pi h. And then again, we've reached the quote-unquote new stuff. If you'd like to get the r by itself, that requires a square root of both sides. The square root of r squared is just r. I'm in the middle of an equation, so I'm going to need a plus or minus. And then much like the last problem, I don't know what v is, I don't know what h is, and I am not going to square root pi. So I'm going to leave it just like that. And that, my friends, is the conclusion of 3.3. Clearly, we didn't utilize the whole 3 hours for this, but we clearly could have. I don't want to drag it out and do like 4 examples of every type, but I think you all can respect that this is a very, very thick section that's going to require quite a bit of work. So that homework assignment that goes along with this, make sure you know what's going on there. Make sure you know all 4 methods of solving a quadratic. Make sure you know how to go one step further and do the inequality. Make sure you know how to manipulate variables. This is a very important section. Chapter 3 is over, by the way, so this is just a huge component. Any section that gets its own day, I cannot stress to you enough how important that's going to be for you. And especially that next test after we do chapter 4, that's going to be here soon. So make sure you're prepared, doing the homework, asking the questions, doing whatever you need to do to get ready on this. Math is like any sport. You get better at it with practice. It's going to take practice, so do what you need to do to make that a reality. If there are any questions, I'll hang back for a bit. You can gladly chat them or type them in the chat or ask me. Otherwise, have a great day. Get on that homework. And remember, Wednesday's lesson will be here tomorrow at 9 a.m. if you're available. Otherwise, it'll be posted just like this one will be. Have a great day, folks.